Okay, I told you in the beginning of this, after organic was over, that we are going to have actually 3 parts to every reaction. Okay, you all listen to this. This is important. 3 parts to a reaction. It's not enough to just know whether the reaction occurs. You have to also know, what do we learn in the kinetics chapter?
When.
Not when.
How.
Not how.
The rate.
The rate, how fast it occurs. Yes, thank you. All right, so you have to know. Thermodynamics told us if a reaction is even possible. In other words, what is it spontaneous or not? Look at the thermodynamics of it as far as the enthalpy, entropy, temperature. That tells me, once I look at those 3 things, I get the delta G and I find out if the reaction is possible. Okay, I know the reaction is possible, but you know what? I could burn a diamond. I could burn a diamond and it's basically exothermic, and its Gibbs free energy is like negative 396 kilojoules per mole. Why don't I burn a lot of diamonds besides the fact they're expensive? Because it's really slow. Okay, it's hard to burn a diamond, even though more energy is given off than you put into it. It's very, very slow reaction. So we have to look at the speed. But let's just say now I've got a thermodynamically favorable reaction, and it's fast. Does that mean I could do the reaction and I'll have no problems with it? Unfortunately, not. There's a 3rd factor involved here, and that is equilibrium. All right, we saw a little bit about equilibrium in the past, but let me just show you something, what you might think about equilibrium right now, and what turns out not to be the case for the vast majority of reactions. Okay, take a look at this picture here. And by the way, a reason I added this, by the way, a reason I'm taping this today, I've actually probably taken this class every single year since I've done it, because every year I decide to add something else because of AP. AP is big into now not only graphs, but models, molecular models of things. Okay, so I want to show you this from a molecular standpoint and from a graphical standpoint, and I've added actually quite a few graphs. If you were to look at AP exams, which I've given you some from 98 and 93 and 2004 and whatever, the older exams generally don't have this model and graphical analysis of the concepts. It sticks with mostly just words. You know, the short answer questions, the free response questions from those years, they're generally fit on like 4 sentences, you know. Now they take an entire page, they've got a graph here, they've got a chart here, they've got data here. It's way more involved than it used to be. So I need to go over that stuff with you. Thank you for turning your phones off.
Why are you looking at me?
Anyway, okay, take a look up here. So if I think about the picture of a beaker of molecules, okay, I'm going to do a reaction. A is going to get turned into B. Now you guys, this guy's purple and that guy's green. This guy's A, that guy's B. That's where we're going to go. We all know from kinetics how this is going to happen. Let's take a look at it from a pictorial standpoint and from a graphical standpoint, how this will happen. In the beginning, this will happen very quickly. Okay, a lot of them get turned over. Then not quite as many per unit of time. It slows down over time. So the reaction rate's very fast in the beginning. Watch the graph. Very fast in the beginning, the reaction rate. But then it slows down. We're used to seeing this graph, and we're used to seeing this graph. You guys had to plot those kind of graphs on the worksheets and on the test the other day. Now, nice part about that, it all fits real good, but it's not really what happens most of the time. Most of the time, reactions do not go to completion. They don't go all the way down to 0. Because before that ever happens, something called equilibrium happens. See this arrow? It's not just going one way. It's going both ways. And that's the kind of arrows you're going to be seeing me write from this entire chapter, and actually for the next 3 chapters. Okay? Let's talk about equilibrium. All right, and I'm going to also do it graphically as well. But first, I'll tell you a little story. Okay? I always use this as my analogy for equilibrium, because they all think of equilibrium as being like a balance. And I used the balance last year. Remember when we did equilibrium on phase equilibrium? Talked about pressure and volume changes? I'm sure you don't remember a whole lot about that, but I did have a balance. A balance is a static equilibrium, but it's not really a good example of the kind of equilibrium I have here. This is a better one. I might have used this last year. You don't have to stop me if I did, because I'm going to use it again. Let's say I've got this construction crew, okay, working on a building site. And there's a pile of bricks on one side of the building. And then there's a foreman over on that side. He says, well, you know what? There's a pile of bricks over on the other side of the building. He tells his workers, Stan, I want you to take these bricks over to the other side and put them in one pile so we don't have 2 piles. That way it'll be the other foreman's problem. Meanwhile, the foreman on the other side says, you know, we got 2 piles of bricks here. Let's get rid of this pile. You take it over to the other side. So he tells his worker, hey, Stosh, I want you to take these bricks over to the air side. So all day long, 8 hours in the day, besides lunch, Stosh and Stan walk back and forth. They each pick up 2 bricks. They walk past each other for 8 hours. How you doing, Stosh? Good. How you doing, Stan? How the kids? All day long, they walk back and forth. Now, at the end of the day, what happened to the piles of bricks, assuming that Stosh and Stan walked at the same pace? Nothing. All right? That is equilibrium. That is dynamic equilibrium. Notice every time they go over there, they're probably picking up 2 different bricks. But they're not picking up the same 2 bricks, but there's no net change because they're working at the same pace. So if we look at this graphical representation, okay, again, A plus 2, I have to use these colors because it goes with the colors that are going to be on here, A and B, okay? Pretend that A are the red molecules in this thing and the B are the blue ones, okay? Take a look at this guy. Watch it. Just watch it for a while and see what's happening. At any given time, guys are either breaking apart, like that one did, or they're coming together. Same guy, they come together, they break apart. If I stop this at any given point, all right, I've got some guys who are together and some guys who are just breaking apart or who are just broke apart. If I let it go a little longer and stop at some other point, I've got guys who are together and guys who are broken apart, okay? And it's happening all the time as these guys mix together. That's equilibrium. So you never get to, here's what you're used to thinking. Here's what you think's happening. You think A plus B, the rate's going down and down and down and down. Eventually, all of A becomes AB2. So at the end, I've got 0 of this, 0 of that, and all of this. 1 mole of that if I put in 1 mole of these guys. No, that's not what happens. At any time in equilibrium, I have, that was a bad place to stop, but here, I've got some guys who are together, I've got some guys who are apart, and they're constantly breaking apart and coming together. Okay? Think of Stosh and Stan walking back and forth, constantly picking up 2 different bricks and moving those piles, but not really moving them. There's no net change. That's equilibrium because both reactions occur. Last chapter, I was only talking about going one direction. And it's true what I said about it. If I have a reaction that goes to completion, it will look like that. It will happen fast in the beginning, and it will end, if it goes to completion, it will end with 0 of this. But that just doesn't happen very often. All right? So let's get some notes now. Now that I've explained that a little bit, let's get some notes trying to show it to you with numbers. I showed it to you graphically. I showed it to you with models. I want to show it to you with numbers as well and with words. Okay? Chemical equilibrium, that's what we're talking about today. So if you haven't figured it out by now, chemical equilibrium is when you have 2 opposing reactions occurring simultaneously at the same rate. Whether it's 2 guys walking back and forth carrying bricks, 2 molecules coming together and then separating apart, 2 reactions happening at equal rates at the same time, and they're opposing each other. Now, one word you like to use here that describes the kind of equilibrium you see in chemical equilibrium is the word dynamic. You know, the word dynamic we don't usually think of. We think of as meaning like a dynamic personality. Dynamic really just means changing, constantly moving. Okay, it's called a dynamic equilibrium because neither reaction actually stops. Both reactions are happening, but there's no net change. No net change. Now, I've shown it to you with pictures, and I've shown it to you with a graph. I want to show it to you with numbers and see if that, you know, because everybody thinks differently. And it's my job to try to get this concept across to you however you happen to think. Some of you would rather pictures. Some of you would rather math. Some of you would rather, that's why I'm going to have the numbers in here. Some of you would rather see things graphically. It's okay for you, all right, to see that stuff that way. So I'm showing it to you in multiple ways here. Let's take a look at an example like this. Copy this guy down. Now, before you copy it, let me explain something. Stop what you're doing right now. I want you to leave a large space for this arrow between B and C. So A plus B, and then a big space like I have here, and then C, because I'm going to draw some stuff in between here that's going to hopefully illustrate what's going on. So leave a very long space between B and C. And a double-headed arrow there. Okay? You may remember seeing this graph before, this same thing I did yesterday before, or last chapter before. Remember me doing this? If I said if I have an initial amount of A, let's say I make up a number. I make up 4 moles of A. I may have used these same numbers. I don't know. And if I have 4 moles of A and 4 moles of B come together, and that's what I put in my beaker, before they actually touch, before they hit, how much C do I have? 0. Agreed? Okay. You may remember doing this. Now, let's wait a certain amount of time. In the beginning, when I only have A and B are going to be smashing into each other very often. Remember the collision theory. Effective collision. You need to hit. You need to hit with enough energy, okay, and the right orientation. Well, if it's all A and B and there's no C, then they're going to be hitting pretty often, okay? So at first, we'll time it after time X. Let's say I've used up half of A and B. How much C did I make? Be careful, because the first mistake we made back in the kinetics chapter was to say 2 plus 2 equals 4. 2 plus 2 does not equal 4. Remember this? If I used up 2 moles of A and 2 moles of B, it came together to make how many moles of C? 2. That's your stoichiometry, right? And I explained that to you. I even showed it to you with the model as well. All right? 1 carbon and 1 oxygen came together to make 1 carbon monoxide. 2 moles of carbon and 2 moles of oxygen would get together to make 2 moles of carbon monoxide. Okay. So far, so good. Next thing I was trying to get across to you a month ago was this. You might think, before that chapter, that after time 2x, this is going to be at 0. You might have thought that. But you'd have been wrong. Okay? What happens after time 2x? Does it go down to 0? Or is it all gone now? Why? Because the rate was a certain speed between here and here. But now, it's going to be half that speed, right? Because you have half as many reactants. So I might have 1 mole of A and 1 mole of B coming together. How much total C will I have now? 3. Because I have 1 more on top of the 2 I already had, so now I've got 3. Everything so far is going fine. We've seen this before, and no one's surprised by this. Here's the crazy part. If I were to go to time 4x, time 8x, times 10x, times infinity x for this reaction, guess what happens? Just watch this. Don't copy it down. Just watch. Why is there no change? Why is there no change? Why does it just stop there? What happened? Equilibrium was reached, and it didn't stop. It's just the 2 rates were now equal. Let's take a look at what's going on. If you can't see it from the numbers, let's draw in some arrows. Okay, watch. I'm going to use a yellow arrow here, or orange, I mean. It seemed to work pretty well. You can see it on the, I was looking on the TV, you can see it better than you can the blue or the red. And then I'll use the green for the other one. At first, when there is only A meeting B, at the instant they meet, I only have a reaction going one way. So just draw a straight arrow going that way. It fills up the entire length of this. What happens to the size of that arrow? What happens to the rate after this by the next time? It's going to be much smaller, right? It's going to be about half the size. Right? What happens to the forward rate next time? Even smaller. All right. Now let's see. Here's the difference. When I was doing this in the kinetics chapter, all I said was it was only going one way. That's not true. Turns out, A and B can get together and make C, but C can also break apart and make A and B, like you saw in that little animation a minute ago. So, let's see. What's the initial rate of reaction of C breaking up in the beginning when there's no C there? What's the rate of reaction? 0. I have no arrow that way, right? By the way, let me erase this guy here. So you don't confuse you. Okay? So I have no C at first. I only have the reaction going that way. But after I've made some C, guess what? Some of that C can start breaking up. Okay? Now don't make that arrow as big as this orange one, because it isn't yet. But as time goes on, and I get more and more C, what happens to the rate of C breaking up? Concentration of C increases, the rate increases, right? We know that from kinetics. So eventually, these two rates grow to the point where they're the same. This one probably could have been technically a little smaller, like that maybe. So as the green one gets bigger and bigger, and the orange one gets smaller and smaller, eventually they get to the point where both of them are the same size. And they remain that size forever. They don't change after that. Those two rates stay where they are. But notice what I said, guys. The two rates stay where they are. The rates aren't changing, but they're constantly being some change. There's some change going on there. You're constantly changing. You're just not changing the net amounts of these guys, net concentration. So does that make sense to anybody? These are three ways of trying to show you the same thing, equilibrium. Now, the last way I'm going to show it to you is the way I have to do it for posterity. So that 2 years from now, when you open this up, you're not just going to see arrows and charts, which you're going to draw some of those charts from before. You're going to draw some of these in a little bit. You're not just going to see arrows and charts and numbers. You're going to have words. So you have to write this down as well. So underneath this, the explanation. As a reaction proceeds, the concentration of the reactants is decreasing. And therefore, the forward rate's getting smaller and smaller and smaller, as you saw with the forward orange arrow. Got smaller and smaller and smaller. That makes sense. That really, up till now, just using that sentence, that's exactly what you'd expect from kinetics. Nobody's surprised by that. What's different now is that the reverse rate. We have to talk about the fact that these guys are reversible reactions, not just going one way. And so what's going to happen there? Meanwhile, while that's getting smaller and smaller and smaller, the green one's getting bigger and bigger and bigger. Okay, so meanwhile, write that down. Meanwhile, the concentration of the products is increasing, and therefore increasing the reverse rate. Eventually, both rates are equal, and you have equilibrium. I know that's a lot to copy, but hopefully you're almost done. We're done with that right now. Okay? But that's key that we have to eventually write this down because, you know, again, 2 years from now when some of you guys are taking chemistry, maybe 1 year for some of you, maybe 3 years for others, you're not going to remember that by just looking at these arrows. Maybe never for most of you, I suppose. Anyways. All right, so you have to have some explanation. All right, does that make sense? I think it does. Now, let's look at some other ways we can see this stuff graphically, okay? You don't try copying these now. I'm going to have you deliberately copy. I'm saving until I've got over this, which ones to copy and how to copy it. First off, a graph of rate versus time will always look similar. A graph of rate versus time is always going to look kind of like this. When I say similar, I mean, here's the key about similarities. They're always going to end up being the same, okay? But you'll notice these are a little bit different. And they can actually be different as far as their height goes, all right, or as far as which one's the forward and which one's the reverse. Let me explain about both of them. Let's start with the forward and reverse part of this, okay? In this reaction, let's say I was just doing A plus A yields B. Just a nice, easy equation, okay? Just A yields B. If I gave you this as a graph, I want you all to listen to this. This is a thinking question. What did I put into the beaker to start off this reaction? A or B? To start the reaction, what did I put into the beaker? Everybody see why the answer has to be A. Because look at the rate in the beginning. of B. What was the rate in the beginning of the reverse direction? What was the rate of the reverse direction? 0. So there couldn't have been any B there. You see what I'm saying? Now, if I hadn't put this graph up here, you saw that on the AP exam, you'd be like, no idea. But it's really a very easy question, if you think about it. Look at this guy. Who must have been put into the beaker for this guy? You see why it had to have been B? Because what rate starts out really fast? The reverse rate. So I must have put B into the beaker, and it eventually reached equilibrium when the two rates were equal. Okay? You see? And every graph of rate versus time will end like this, together. That's equilibrium. But that's not what the graph of concentration versus time does. Oh, and by the way, these graphs of rate versus time may not be always right smack dab in the middle, because it will depend on the coefficients. We'll talk about that later. We're not going to really confuse you with that right now. Some of these rates, remember the coefficients, if the rate's, like a guy has a coefficient of 4, and the other guy's a coefficient of 1, his rate, the guy with 4, is going to actually be dropping much faster, kind of like when we made the sandwiches. I was talking about making sandwiches. That was a long time ago, I know, but we'll talk. Don't worry about that right now. Now, if I do a graph of concentration versus time, that's different. Okay? Now, granted, notice the concentration versus time is not going to look like this anyway. Because what would this guy have done? If he looks like that, let me just show you a better example, like right here. If he goes all the way to 0, okay, and this guy goes to whatever the maximum he can get to, that will be a reaction that would have gone to completion, okay, went all the way to 0. Most of them don't look like that. What would they look like, you might ask? What would an equilibrium graph like this look? I've been used to seeing these kind. We've been drawing these kind. But I just got done telling you for the last 20 minutes, that's not what most reactions do. Most reactions would look like that. See the difference? Does that make sense? And it's not just that ugly. Remember, I'm going to have you draw some of these, but not right now. It could be uglier than that. Take a look at some of these. That's for an equilibrium one. Look at this guy. That's an equilibrium one. This is an equilibrium one where it reached equilibrium really fast. Here's one where it went almost to completion. You see the difference? Can you see what the graph is saying? I'm getting some, most people I'm nodding heads, but not everybody. All right? Let me explain something about, let's go back for a second. Maybe you don't quite understand this, but let's go back to this guy right here again, okay? Just for a second. And let's just draw my arrows in here. The forward direction in the beginning is just that guy. He gets smaller and smaller. The reverse direction, 0, he gets bigger and bigger until they're equal. That's how I showed this guy. But it didn't have to happen that way. You know what could have happened? It could have happened that the reverse direction is so much faster than the forward direction that putting in 4 moles of A and 4 moles of B, once I got down to 3.99 moles of A and 3.99 moles of B, and I just made 0.01 moles of C, it was already equal. They're already equal. I don't want anyone to get the idea that this equilibrium happens when you have equal amounts of reactants and products. It's very possible that I could put in to a beaker 4 moles of A and 4 moles of B, come back an hour later, reach the equilibrium, and I'll have 3.99 moles of A and 3.99 moles of B. And only have made 0.01 moles of C. How can that happen? Because the rate of this guy is so much faster than the rate of that guy. It catches up to him right away. Okay? And that's why the graph might look like, I was just showing you a minute ago. Oh, let's go on this again. But, might look like this. See it? Now let me ask you something else about that guy. Who can tell me what the equation for this reaction would be? In the forward direction, what did I start with? What did I start with? HI, H2, or H2I? Or HI, H2, or I2? H2 and I2? Y'all agree he started really high concentrations and I had no HI? So if I ask you again, you're not drawing this one yet, I'm going to leave time to do this. If I asked you to draw the equation for this, you would have written H2 plus I2. That's terrible. H2 plus I2 yields HI. You would have also had to balance it. Is that balanced? No. So you put a 2 in front of that guy. What would you have written for the equation for this guy? HI yields H2 plus I2. Do you see why? You see what's going on here? Okay, I have to balance that again. The reason I started with HI is look how much I've got a lot of HI in the beginning of this reaction. I've got no H. So if I just write left to right, the correct forward direction, the way the reaction's written in this graph, that's the graph. I'm sorry, that's the equation for this graph. That's the equation for this graph. Let me ask you something. If I calculated, well, oh, that's right, you don't know what KC is yet. Let me just ask you this, because I'm going to get to that. That's when we're going to come back to this. Which one of these guys went closer to completion? That guy over there or this guy over here? Everybody agree it's this guy? Yeah. You know, he dropped almost all the way down. This guy got pretty high up. These guys didn't do much of anything, right? So let me ask you this. Which reaction is faster? H2 getting together and making I2, or HI breaking up into here? Well, I heard both answers there. Which is it? I still heard both answers. Which reaction must be faster because it went most of the way? Let's just call it A and B. A or B? Raise your hand for A. Raise your hand for B. Is anybody going to raise their hand? So you think the forward direction here is faster than the reverse direction there. That's what you think. Really? That's an amazing thing. That's an amazing thing. I never would have thought you'd think that. Didn't we just say that this guy went almost to completion? Right? So that means the reaction was happening much more this way, much more that way, and it didn't get to equilibrium, so HI couldn't be happening that quickly. You understand why? Don't you see that? Wow, I'm amazed. I didn't ask that in the last class, so I'm glad I asked it now. Well, hopefully it'll come clearer because I haven't talked about there's a way to calculate this. It's called KC. KC tells us where the equilibrium lies, whether it lies like this one almost towards completion or whether it lies like this one where most of the reactants stay unreacted. Okay? I'm going to get to that in a minute, but let's just get one more graph up here. Maybe this one will make it clearer. Look at this guy. Can you write the equation for this guy? What would the equation for that guy be? N2 plus N2 plus H2 yields NH3. Everybody agree with that? Can you balance it? What do we need here? A 2 here because 2 times 3 is 6. A 3 there, and then what? A 2 there, right?
No.
All right, we don't need anything. Right? Thank you. 3 there? Who said 3 there? You got the first one and the last one wrong. All right. So N2, 3H2, 6. Okay, that's good. Now, look at this guy. What do you think about him? Do you think that reaction went close to completion? No. So you know what that tells me? It tells me that the reverse reaction must be pretty strong. It's keeping it from getting to completion. If there was no reverse reaction, guys, wouldn't it go all the way to 0? Right? If there's no reverse reaction. If there's a stronger reverse reaction, the stronger the reverse reaction is, the more the graph's going to look like that and less like that. Okay? Anyway, that's just thinking-wise. There's going to be a way to calculate that KC very soon because that's what I'm going to talk about right now. Equilibrium constant. That helps us to determine where the equilibrium lies. Do I want to carry out a reaction that's not going to give me any products anyway? Even though it's thermodynamically favorable. Even though it's going to happen really fast. Would I expect that I really want to do this reaction if the equilibrium is going to reach equilibrium? Reverse rate is so much faster than the forward rate. I'm just not going to get any products anyway. Well, there's a way to mathematically do that. And that's what we're going to talk about right now. The equilibrium constant, or what's called KC. Okay? We're going to derive KC. Now, some of you derive to school in the morning, but most of you don't derive KC.
That was bad.
Yeah, that was bad. Yeah. You don't do a lot of derivations, but I have to do this one because it really helps to explain. I don't do a lot of derivations either, and you don't do much in physics or other classes, but this one really helps to talk about what's going on, what Kc really means. All right, so I'm going to go back to kinetics, and I'm going to make a generic equation. Let's say I have this generic equation, AA plus BB yields CC plus DD, where little a's and the little b's, the lowercase letters, those guys are the coefficients of the equation. And A, B, C, and D, the capital letters, they are the they are the reactants and products. They're the guys who are reacting and being produced. Okay? All right. Now, if I assume, and this is a big assumption, if I assume a one-step mechanism, which I can do in many, many gaseous reactions, that's why you'll see a lot of the guys you're going to be talking about are going to be gaseous reactions. If I can assume a one-step mechanism, I can write the rate law expression for each of these guys, can't I? Think about this. Let's say I have this equation. Don't write this down. This is not part of the derivation. Let's say I have an equation like A plus 2B yields C from last chapter. This was the equation from last chapter. Don't write it down, please. And that was the only step, the slow step, right? Wouldn't you all agree that the rate law expression would be rate equals A, K, A to the first power, B to the second power? You all agree that would be the case, right? So, can you apply the same thing to this equation? If it's a one-step mechanism, and this is the slow step, you don't have to write that down. I'm just saying, if that is the only step, my question is, what does the rate law expression look like for this guy? Wouldn't you agree it would look like this? K, A to the A, B to the B. Does that make sense? Right? Notice I put a little KF to distinguish it from the reverse direction, but the forward rate would equal KF, A to the A, B to the B. You're basically just taking your concentration of the reactants, raised to their coefficients. Because it's a one-step mechanism, that works, because if the coefficient of A is 2, he's in the slow step twice. If the coefficient of A is 1, he's in the slow step once. So it makes sense. That is the order of the reactant. Can you think now something new? They go both ways. What would the rate law expression for the reverse reaction have to be? Exactly. C to the C, D to the D. Good. You see now, Michelle, why I wanted you to be here for this period. It's kind of like, this is all the concepts they're getting across here. The actual calculations for this aren't too bad. By the way, that's a little low. There. Well, I mean, the early calculations, they do get complicated. All right. Now, what do we know happens at equilibrium? What can we say about the forward and reverse rates? What are they always going to be? They're going to be equal. Rate forward and rate reverse are going to be equal. So therefore, if this guy is equal to that guy, then wouldn't you not all agree that this guy has to equal that guy? Right here and here? Right? Now, some of you right now are probably saying to yourself, I think we took a wrong turn on our derive because where are we going with all this? It's okay. We are getting somewhere, believe it or not. I'm not just doing this for my health. All right. What I'm going to do now is I'm going to bring all the constants to one side and all the variables to the other and create a new constant. Instead of being the rate law expression constant, little k, we're going to make big K. Okay? 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 Okay. 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 It's pretty bad. So, if I bring, y'all agree, if I'm going to bring KR over to this side, I would divide both sides by KR. And I divide both, I want to bring those guys over there, I divide both sides by AB. And wouldn't you agree that that's what it would look like? Right? Is everybody okay with that? It's just algebra. I mean, that's not, I'm not doing any integrations or any calculus here, people. That's just algebra. There's nothing difficult about that. All right, you all good? Now, guess what that new thing is? KF over KR. Guess what that is?
KC.
That's KC and the Sunshine Band. What was their big song?
Well,
No, that was it wasn't them though. KC and the Sunshine Band. They had a big
Bowie
hit.
died.
David Bowie died. Thank you. Now we can date this video. People in the future watching this video, this is the day David Bowie died.
no, yeah, yes.
Yeah.
All right, it's the day after David Bowie. People in the future are looking at David who? I have no idea who that is.
That's me
Actually,
now.
that's Caitlin right
People
now.
don't know.
David
Just
who?
call me Caitlin.
See the guy that invented that knife?
Don't call me
Why is that funny? Why is that funny? Knife. Bowie knife. You ever hear of a Bowie knife? Maybe not. Okay, that's on TV now. You're immortalized from that sound. Okay. All right, you ready? Now, the thing is, what does KC tell us? Okay, now that we've derived KC, it's driving me crazy. What does KC tell me? I got enough bad derived jokes. KC is basically this. It's a ratio of the forward and the reverse rates. Okay? KF over KR. So what would I expect? If KC is, don't write this down, but if KC is a very large, if it's greater than 1, KC is greater than 1, a very big number. Let's say 1,000. All right? What does that tell me the size of KF is versus KR? Large. KF must be very big, KR very small, so I have a very fast forward direction, a very slow reverse direction. What will happen? I put in 1 mole of this and 1 mole of that. After it reaches equilibrium, almost all of it becomes product, doesn't it? Because the forward direction's so much better than the reverse. Got it? So at equilibrium, I might have 0.001 moles only left of this, and I'll have 0.999 moles of that. You see? If KC's big, no problem. That forward direction's great. If KC's really small, if he's much smaller than 1, what does that tell me? Well, that means this guy's got to be really small, maybe 1, and this guy's got to be really big, maybe 1,000. So now the answer is 0.001. I get a really small KC. The reverse reaction is predominant over the forward. And so I put in 1 mole of this and 1 mole of that. At equilibrium, I still almost have 1 mole of that. I only have maybe 0.99 moles of that. Okay? That's what it's really telling me. Now, in the first, I'm going to get to this charts in a second. But the first questions you have, just 20 to 23, okay, they're asking you to just set up the equilibrium expression for the following equations. It's going to take you literally 5 minutes to do that whole 20 to 23, okay, because say you had this equation. By the way, this is not an equilibrium equation. I'm just using it because you're very familiar with it. Salt, making salt. 2 there, 2 there. This is a reaction that goes to completion. It explosively reacts, you put them together, and you get all the salt from the sodium and chlorine. Okay, but let's say it wasn't. Let's say it was an equilibrium problem, okay? What would the rate law expression be? I'm sorry, what would Kc be? He would simply be NaCl squared over Na squared Cl2 to the first power. Do you see why? Because it's products over reactants raised to their coefficients. You see? That's all you got to write. For 20 to 23, you're going to write that. For everyone, you get an equation like this, you simply put the products raised to the coefficients over the reactants raised to their coefficients. That's all you got to do. But I told you I wanted you to copy some graphs down so you have them for your notes. They're going to be in the worksheets as well. So let's just get this before the bell rings. We don't have much time. Copy this first graph down. Wait, what was that last thing say? Oh, yeah, last thing here, write this down. I forgot, I just added this last year. It's a good point. Now, this I told you already. I said, well, if you're working with gases, we generally have a pretty easy time. And most of the time, your reactions, your problems are going to be gases. But if they want to trick you on the AP exam, they can do this. If the reactant or product that's a pure solid or liquid is not going to apply to that. Okay? You wouldn't include him in there because he's not reacting at that same. You can't get the assumption of the one-step mechanism and he's being used like that. Okay? Now, let's go to the charts. I'm going to be, and I'm not going to trick you. on your tests in these worksheets and these problems, we're going to be given gases. So let's assume all these guys are gases here. Okay, copy these first two charts down. We'll worry about the other one in a minute. Copy those first two down real quick. Don't copy the third one. We'll do that one in a minute. Let me have them just appear. Okay. And the question up here too. Write the correct equation and predict the size of Kc for each graph. So kind of like I just did a minute ago. Do each of those equations. Can you tell me what the equation would look like forward to reverse, left to right, if you were to draw the equation, if all you were given was this graph, or if all you were given was this graph? Write them underneath each, like I did a minute ago. I think all of you can do that. You can write the correct equation, right? Just look at who starts high and who starts 0. You can write the correct equation. Does everybody agree that that will be the equation for this guy up here? That makes sense? Because H2 and I2 started high, ended up low. You have to balance it with the 2 there. And would you expect Kc to be big or small from this graph? Think about it. Who's winning? Who is clearly the better reaction, forward or reverse? Forward. And Kc is clear. Look at forward direction. You used up almost all of your H2 and I2. So it has to be that. And in which case, that's the numerator. That's going to make a large Kc. I shouldn't say Kc equals. Kc is greater than 1. What will this reaction look like? Hi, 2Hi would actually yield H2 plus I2. What would you predict for this guy's Kc size? Very small. Can anybody show off your mathematical intuitive sense? If I told you the Kc for this was 100, what do you think the Kc for that probably is? Very good, Caitlin. You see why? Isn't it just going to be the reciprocal? Because that is the forward direction, and this is the reverse direction flipped around. You see what I'm saying? Hold on, I want you to do that. I know the bell rang, but I purposely wanted to do this class and tape it because I knew I wouldn't have to rush because we have a whole extra period after this. Let's just do this last one. You'll get to go to the lab in a second. Just do that last one here. Do that one on your own. And we'll see if you get what I would say for this guy. You have that for your equation, I hope? You know it's not NH3 yielding N2 plus H2 because NH3 starts at 0. Okay? Would you predict the Kc for this, the equilibrium constant for this guy to be greater than, equal to, or less than 1? Everybody agree? Kc is less than 1. She was afraid to say it, but yeah, Kc would be less than 1 in this case. Remember a minute ago I told you how the graphs kind of end up in different places, depending on, even for the rates, end up in different places? Do you see why that might happen? Look at H2. Look at him. His rate, you see what I'm saying? Since there's a coefficient of 3 in front of him, is much greater than the N2, which is only a 1, and this guy's kind of in between. In other words, the rate of change, because of the coefficients, is actually different. Now, I'm not going to expect that you understand that perfectly right now. We're going to get a lot more practice with this. But right now, do you at least understand how to write the equation and whether Kc would be big or small? That's all I really care about for right now. Okay? All right, good enough.